Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Today we will talk about the intermediate value theorem. Well, let's continue talking about the intermediate value theorem. Activity 2a. We have a curve that represents a function f. This is a, this is d, this is b, this is f of b, this is c, this would be f of c, and this is e, this is f of e. Now I'd like to remind you here that if this is a, this is not f of a because f is not defined at a in this specific case. We have an open point. Okay, the first part asks about the domain of definition and the range of f. So the domain of definition in this case would be the interval AB. We project the curve on the x-axis. Remember, it's open at A, it's closed at B, because here we have an open point and here we have a closed point. While the range we projected on the y-axis, as you see here, the green part, it will be f of c and d. It's closed at f of c and it's opened at d because d is not attained. The second part asks about the number of common points between C and Lm, the line with equation y equals m, where m is a real number. Remember, y equals m is a horizontal line. Let's see Lm. This is Lm, and we need to see the number of common points between C and Lm. So, from negative infinity to f of c open, we can see that we have 0 common points. Now specifically, when m is equal to f of c, we can see that we have only one common point. Let's continue. From f of c to f of b open, we see that we have two common points. Then from f of b to f of e, we have three common points. Then at m equals f of e exactly, we have two common points. And from f of e to d, we have one common point. And finally, when m belongs to d closed plus infinity, we have 0 common points. So we can see from here that sometimes we have 0 common points, sometimes we have 1 common point, 2 common points, and 3 common points. What are the conditions that should exist so that this equation of x equals m has one or more roots? Now we can see that f should be continuous and m, this point, should belong to f of I. You see, if m belongs to f of I, it means somewhere here on the green segment, you can see that f of x equals m has one or more roots. Otherwise, if m doesn't belong to the green part, which is here, I mean it's somewhere here or somewhere downward, we can see that the line Lm doesn't cut the curve, and this is very logical. Activity 2b, we have this curve. We need to find the domain of definition and the range of the function. Well, this is A, this is B. This is the domain of definition, which is A, B closed. Let's continue. If this is A, this would be f of A, and if this is B, this would be f of B, and the range would be the green part, the green segment, which is f of A, f of B. And in fact, this happens because the curve is strictly increasing and continuous. So to find the range of the function, we just apply f of A here and f of B here, being a closed interval. Now find the number of common points between the curve C and the line Lm. Let's see, this is the line. we can see that we have no common points. Then from f of a to f of b we have only one common point, and then from f of b open to plus infinity we have 0 common points. So again, what conditions should exist so that the equation f of x equals m has a unique root? Now, to have a unique root, what is the condition that we should have? In fact, f should be continuous, strictly monotonic, and m belongs to f of I. And this is in fact the most important condition: m belongs to f of I. Remember, if m is somewhere here on the green part, then the curve and the line would intersect. Otherwise, if m is not somewhere here, we can see that the line doesn't intersect or doesn't cut the curve. Let's continue. We have this curve, which is a strictly decreasing curve. We need also the domain of definition. The domain is closed A, closed B, and the range is closed f of B, closed f of A, and this happens because the curve is strictly decreasing. We know it from before. Then we need the number of common points between L, M, and C. You see? Now, so far, they don't have any common point. Then, from f of b to f of a, they do have one common point. And from f of a till plus infinity, they don't have any common point. Again, what are the conditions that exist so that we have a unique root? In fact, f should be continuous, strictly monotonic, and m should belong to f of I. Let's see the results. F is a given function which is defined on an interval I. M is a real number, any real number. If f is continuous, f is strictly monotonic on I, and m belongs to f of I mean the range of the function, then we can see that the equation f of x equals m has a unique root alpha. You see here? So this is an increasing function, and f of x equals m in this case has a unique root because m in fact belongs to the range. Now this would be alpha. Remember, alpha plays the role of x. Let's see property 4. Let m be a real number and f a given function defined on AB if the equation f of x equals m has a unique root alpha, and if f of a is smaller than m and f of b is greater than m. Let's see it here graphically. This is a, and this is f of a. This is b, you see, and this is f of b. You can see that f of a is smaller than m, and f of b is greater than m. If one of them is smaller than m and one of them is greater than m, then we can say that alpha is between a and b. You see here, this is alpha and it is between a and b. Remember, alpha is a root of the equation f of x equals m if and only if f of alpha is m. Now, we're going to have another case. If f of a is greater than m or f of b is smaller than m, then we get the same result. And we're going also to see it graphically, and this is what happens, in fact, when the function is strictly decreasing. You see, again, this is f of x equals m, which cuts the curve in one point only. Now, this is alpha. If this is a, this would be f of a. And if this point is b, this would be f of b. And we can see that alpha is between a and b. But in this case, remember, f of a is greater than m because it's above m, and f of b is smaller than m because f of b is below m. Now, these are the properties that we've seen so far. All of these properties are called the intermediate value theorem properties. In fact, properties 3 and 4 are the main properties, and properties 1 and 2 are specific cases of 3 and 4. So let's see very quickly. If f is continuous, strictly monotonic, and f of x changes signs, then we can say that f x equals 0 has a unique root alpha, and if if f of x equals 0 has a unique root alpha and f of a times f of b is less than 0, we can state that alpha is between a and b. Now, more general, if we want to generalize these two properties, if f is continuous on I and f is strictly monotonic on I and m belongs to f of I, and this is very important, then we can state that the equation f of x equals m. Now, whether m is 0 or not, it doesn't matter. It has a unique root alpha, and we can continue also if f of x equals m has a unique root alpha, and if f of a is less than m and f of b is greater than m, or f of a is greater than m and f of b is less than m, then we can say that alpha is between a and b. Let's take this application. We have a table of variations of the function x cubed minus 3x plus 2. The question is to prove that the equation f of x equals 0 has two roots, one of which is theta, such that theta is between negative 2.1 and negative 1.8. Now here, because we want to prove that f of x equals 0 has two roots, we have to go back to properties 1 and 2, because they are specific for 0. Let's see. From the table, we can see that f of 1 is 0, so we can automatically say that f of x equals 0 has 1 as a root. So this is the first root. So on the interval negative infinity, negative 1, somewhere here, we can see that f is continuous, f is strictly increasing, and f of x changes signs from negative infinity to plus 4. So from these three conditions, we can tell that the equation f of x equals 0 has a unique root, theta. So by now, 1 is a root and theta is another root, so we proved that the equation has two roots. Now we need to verify that the second root theta falls between negative 2.1 and negative 1.8. So we just calculate f of negative 2.1 using the explicit form of the function, which is negative 0.9, which is negative, and f of negative 1.8, which is 1.5, which is positive. So we can say from here that theta falls between negative 2.1 and negative 1.8. Finally, we can state that f of x equals 0 has two roots, 1 and theta. Now let's see the second part of the question. We need to prove that the equation f of x equals 4 has two roots, one of which is lambda, such that lambda falls between 1.8 and 2.1. Again, f of negative 1 is 4 from the table, so we can say that the equation f of x equals 4 has negative 1 as a root. Now to search for the second root, remember now we need f of x to be equal to 4, so we are somewhere here, because 4 plays the role of m. Now on the interval 1 plus infinity, you see somewhere here, we can see that f of x could be equal to 4, because 4 falls between 0 and plus infinity. You can see that f is continuous, f is strictly increasing, and 4 belongs to f of I, and this is very important, as I said before. Now, what is f of 1 plus infinity? What is the image of the interval 1 plus infinity? It will be the interval 0 plus infinity. And this is very logical because, in fact, 4 belongs to 0 plus infinity. So from these three conditions, we can state that the equation of x equals 4 has a unique root, lambda. So negative 1 is a root and lambda is another root. Now we need to verify that lambda is between 1.8 and 2.1. We just find f of 1.8 using the explicit form of the function, which is 2.4, which is less than 4, and f of 2.1, which is 4.9, which is greater than 4. Now, because one of them is smaller than m and the other one is greater than m, we can state that lambda falls between 1.8 and 2.1. So the equation of x equals 0 has two roots, negative 1 and lambda. Now Rami or Mira, we have a table of variations of a function f, and we need to find the number of roots of the equation f of x equals 0. Now how many roots does the equation of x equals 0 have? Let's see, Rami. On the first interval, which is negative infinity 0, f of x equals 0 has no roots, since its minimum is 2. So here it has no roots because its minimum is 2. And on the interval 0 plus infinity, somewhere here, f of x equals 0 also has no roots since its maximum is less than 0. And Rami stated that 0 in this case is not attained. So 0 is not attained. Thus, f of x equals 0 has no roots. Let's see Mira. Mira stated that on the interval negative infinity 0, here, the equation f of x equals 0 has no roots since its minimum is greater than 0. This is similar to what Rami said before. Whereas on the interval 0 plus infinity, f is continuous, f is strictly increasing, and f of x changes signs from negative infinity to 0. Therefore, the equation f of x equals 0 has one root. Now, what do you think about these two arguments? Well, I think Mira's argument is not correct because in fact f of x in this case doesn't change signs. Remember, negative infinity is negative, but 0 is not positive. It could be 0 minus, which is negative, or 0 plus, which is positive. And in fact, in this case, it's 0 minus. So I agree with Rami that the equation f of x equals 0 has no roots. If we just analyze it from the table, this is f of x. It varies from 2 plus to positive infinity and from negative infinity to 0 minus. It can never attain 0. Thank you.